I hope you have seen my video on how carbon is formed in stars and supernova explosions. Carbon bonds are critical to life, so the study of carbon bonds is a critical lead into organic chemistry and the life sciences. The simplest carbon-based chemical is carbon itself. Pure carbon can exist as graphite and diamond, amorphous carbon and fullerenes, and laboratory-formed carbon nanotubes and laboratory-formed graphene. Graphite forms in one-atom-thick planar sheets of hexagonal-linked carbon atoms. The graphite sheets are layered and held together by van der Waals bonds. The graphite sheets are strongly linked in the planar direction. The van der Waals bonds are easily broken and so allow the planar sheets to slide past one another. This sliding property of its sheet layer over each other makes graphite very useful as a dry lubricant and as pencil lead. In addition, graphite is also a good conductor both of heat and electricity. Graphene is a laboratory effort to extract graphite as a single layer. If techniques are ever developed to make production economical, graphene might be useful in making useful products such as ultra-thin computer screens that can be rolled up into a tube when not in use. Diamond forms when graphite is crushed at great temperature and pressure. Diamonds have a tetrahedral or three-sided pyramid crystal structure and are the hardest known minerals. Besides being used in jewelry, tiny diamonds make excellent abrasive materials. Diamond is an excellent thermal conductor, but a poor electrical conductor. These two opposing properties make diamond useful in cooling electronic equipment without providing a path for a short circuit. Natural diamonds form from carbon deposits deep in the Earth's crust. Diamonds are brought closer to the surface of the Earth by tectonic activity such as earthquakes and volcanoes. An obvious extraterrestrial source of diamonds are supernovas. Nanodiamonds have often been found in meteorites. Amorphous carbon can be either crushed graphite or soot, or carbon black products of incomplete combustion. Fullerenes are nanometer-sized, spherical, or ellipsoid-shaped cages of a single shell of carbon atoms. Fullerenes are often products of incomplete combustion. Carbon nanotubes are laboratory-formed single-sheet graphite in a cylindrical shape that forms a tube of undefined length. The tubes are flexible and very strong in tension. If techniques are ever developed to make large numbers of very long nanotubes, the cables that could be developed from bundles of carbon tubes might revolutionize building construction and even the development of a space elevator that can run up and down on a carbon nanotube cable. Concentrated carbon is most commonly found in Earth as coal and oil. Most coal is believed to have formed from trees and plant material of ancient swamps. In fact, the entire geologic time period, from 360 to 300 million years ago, is known as the Carboniferous period. Early in the Carboniferous period, the Earth's average temperature was 68 Fahrenheit or 20 Celsius. The Carboniferous period's mean global temperature was 10 Fahrenheit higher than today's mean global temperature of 58 Fahrenheit or 14.5 Celsius. With all this plant life, the oxygen level in the atmosphere climbed to 35%, much higher than the current atmospheric oxygen level of 20%. There were no glaciers, and much of the land in the tropics to the mid-latitudes were covered in swamps or shallow inland seas that teemed with plant life. Even in the mid-Carboniferous period, when some cooling caused the glaciers to return to the poles and the inland seas to retreat, the mid-latitudes and tropics were covered in swamp and tropical forest. When all this plant life died, it fell to the bottom of the swamps and seas and did not fully decompose in the low oxygen mud and slowly changed to peat. Towards the end of the Carboniferous period, the continents came together to form the supercontinent of Pangaea. Mountains grew. The swamps dried up and were covered with sediment. Over millions of years, the buried peat was compressed and converted to coal. In the coal we mine today, we often find fossilized remains of trees and animals that lived in the Carboniferous swamps over 300 million years ago. Oil was also formed millions of years ago from the remains of plankton and algae that sank to the bottom of the ocean and was covered in sediment. Oil starts out as the hydrocarbon kerogen. If it remains cool, it will remain as kerogen. If the kerogen is subjected to warmth, it will be chemically converted into petroleum. If liquid petroleum gets too hot, it will be chemically converted into natural gas, mostly methane. The presence of fossils in coal favors the argument that most coal is the product of decayed plant matter. It is argued by some scientists that deeper deposits of coal and petroleum are abiogenic, not a product of life. It is agreed that at least some petroleum deposits are abiogenic. From Wikipedia, the controversy isn't over whether abiogenic oil reserves exist, said Larry Nation of the American Association of Petroleum Geologists. The controversy is over how much they contribute to Earth's overall reserves and how much time and effort geologists should devote to seeking them out, he said. We know that carbon originated in red giants and was blasted into space by planetary nebula or by supernova explosions. At some point, 5 billion years ago, some of this remnant dust and gas from an exploded star began to collapse under its own gravity. Perhaps a passing star or the shockwave from another supernova triggered the collapse. The dust must have had some amount of swirl or angular momentum. As it collapsed, an accretion disk formed. More than 99% of the dust and gas in the accretion disk collapsed into the center and formed our sun. Most of the remaining dust and gas was swept up by the forming protoplanets. The remainder of the accretion disk that was too sparse to collapse into planets remains as cometary material in the Kuiper belt beyond the orbit of Neptune. Beyond the Kuiper belt is the Oort cloud that extends out many light years to touch the remnants of dust clouds that survive the formations of neighboring stars, such as Alpha Centauri. We can imagine proto-Earth swept up great chunks of dust and larger planetesimals that were trying to grow into planets that were never to be. We can imagine among the star debris that the proto-Earth was accumulating were great chunks of raw carbon. We can say that a lot of this carbon has been recycled through the life that eventually formed on the Earth into coal and petroleum. How much of the raw carbon lies buried miles deep in the Earth's crust, undisturbed from the debris ejected by the exploding red giant, we cannot say. It is probably some, but not a lot. Most of the Earth is molten magma, thousands of miles thick. The Earth's crust is only the outermost 5 to 25 miles of this molten material that has solidified into solid rock. The solid rock that forms the continents has been subjected to being remelted and reabsorbed into the molten magma beneath in tectonic processes. It is doubtful that much, if any, of the original chunks of carbon blown into space from a primordial supernova has survived the tectonic processes that formed and continue to reform Earth's crust to today. In 2017, a seismic anomaly that geologists believe may be a molten carbon lake was discovered 200 miles deep below the western United States. This molten carbon lake is far too deep in Earth's magma layer to be accessible with current drilling methods. The molten carbon lake is nearly 700,000 square miles in area and may contain 100 million metric tons of carbon. By comparison, the EPA estimates global carbon emissions each year are nearly 10 billion metric tons. The CO2 trapped in this molten carbon lake will eventually be released into the air over thousands of years by volcanic eruptions in the western United States volcanoes. The carbon atom is a prime candidate for a building block for life because it has 4 valence electrons and so is able to bond with 4 other atoms simultaneously. Carbon likes to bond with itself to form rings or chains. These chains can be hundreds of carbon atoms long. A favorite bonding partner is hydrogen, thus forming hydrocarbons. Hydrocarbons should be very familiar to anyone in the oil and gas industry, as well as plastics engineers. So, we see how readily carbon with its 4 valence electrons can form long-chain hydrocarbon molecules. The ability of carbon to form chains that helps carbon form plastics is useful to build the complex molecules that are needed for living organisms. Silicon, germanium, tin, and lead are members of the same periodic group as carbon, and all have 4 valence electrons and are also capable of bonding with 4 other atoms simultaneously. Certain scientists have proposed that silicon could also be a candidate as a building block for life. Science fiction writers have used silicon as a basis for life in their writing, most notably in the Star Trek The Original Series episode, Devil in the Dark, where the devil turned out to be a silicon-based creature known as a Horta. Also in the Star Trek The Next Generation, the episodes The Silicon Avatar and Home Soil had silicon-based life forms. All life on Earth is carbon-based life. We cannot rule out silicon-based life straight away. Silicon can bond with 4 other atoms. Silicon is the 8th most common element in the universe and the 2nd most common element on Earth. Silicon-based clay crystals have an inorganic means of multiplying, which has led some serious scientists to speculate the first life forms on Earth were silicon clay-based rather than carbon-based. Given the pros of silicon as a possible building block element, there are some serious cons. For example, the most common form of silicon on Earth is silicon dioxide, SiO2, found in quartz rocks and silica sand. Unlike carbon dioxide, which easily dissolves in water under the pull of hydrogen bonds, silicon dioxide is a tightly bound solid that resists interacting with most other solvents and chemicals. Some plankton and sponges do make their exoskeletons out of silica that they extract from seawater, but the silica is used as a structural element and takes no part in the living functions of plankton or sponges. Silicon does form bonds with hydrogen. These hydrogen-silicon compounds are called silanes. Silane SiH4 is a gas, the silicon equivalent of the carbon-based methane CH4. Silane can form rings containing up to 7 silicon atoms, known as heptasilanes. However, hydrogen-silicon rings or chains of more than 7 silicon atoms are difficult to achieve because silicon-based silanes are thermally unstable and tend to dehydrogenate or break up into smaller silane rings while giving off hydrogen gas. Carbon-based alkanes and polymers may form nearly infinitely long chain lengths. Silicon-based silanes do not seem to be practical for forming the complex molecules needed for life. In contrast to silicon-based silanes, carbon-based alkanes are very practical for making fuels and plastics for the petrochemical industry, as well as forming molecules for life.
Thank you for watching. If you enjoyed this video and want to help me make similar content, please like and subscribe.